so in this video is kind of similar to the one I did with capacitors, but now we're working with resistors. And basically we will learn that there are rules for adding resistors when they're in series and in parallel. I always think about it when I'm thinking about adding them and comparing them to capacitors, that the rules are basically switched in terms of how you add up the resistors compared to how you add up the capacitors. But you don't have to use that as your goal. But we learn that when you have resistors in series, to find their equivalent resistance, you simply add them, and that gives you the equivalent. One of the reasons that this is true is because two resistors in series have the exact same current running through them, and if they're the only resistors, they'll be the same as the current that comes from the battery. As you go through the resistor, each resistor will produce a potential difference. Those two will add up to be the total potential difference. Once again, if it's only two resistors connected to the battery, that will be equal to the potential of the battery. Now, when we have resistors in parallel, in order to find the equivalent, we add the inverses of the resistors, and that gives us the inverse of the equivalent. When you have two resistors in parallel, they actually have the exact same potential difference across them. What that does is it means that when you get to the branch where you can go through the two paths to either go through this resistor or that resistor, there really isn't a preferred path because it represents the same potential obstacle, if you will, so that's why they're the same. But because of that, the current, as it comes to that branch to go through the two parallel branches, will actually split. So there's a certain amount of current coming in, it'll split into the two parallel branches, and the way that the current branches is to maintain the same potential difference across each resistor. Basically, these rules come from just sort of understanding, for instance, mainly the current is important because whether the current has a chance to change or not will determine what the rule is for that particular arrangement. And then everything else then kind of comes from Ohm's law. One of the reasons that the rules for adding the resistors in series and parallel is different from capacitors is simply because the governing expression that relates all three of the quantities that we're interested in is different. Remember, capacitance was Q over V, where this is simply more of a linear relationship. So, as an example, as I did before with capacitors, I want to take a series or a combination of resistors that has resistors in series and in parallel and put them all together. And let's see how we would simplify this circuit in order to be able to determine eventually how much current goes through each of these resistors and what is the potential difference across each one of them. As we do that, we'll be using the rules for adding resistors, and then we'll also be applying the rules for current and voltage. So as we did with capacitors, the first thing that we want to do is we want to pick the most complicated part of the circuit. And so we're going to look at this top of this. These two branches are in parallel, but at the top we have two in series. And so the equivalent of those two is simply found by adding the two, and that gives us 20 ohms. And so we can replace those two resistors in series by a single resistance that has 20 ohms. So we're going to do that. So we've only done a little bit here, and we've replaced the two in series by a single resistor that is the equivalent. And now what we want to do is we want to deal with this entire parallel branch, the two that are in parallel with each other. And so let's find the equivalent to that. I get 1 over the equivalent would be equal to 1 over 20 plus 1 over 60. I can actually find a common denominator here, and so I get 4/60. And so my equivalent to those two in parallel is actually a 15 ohm resistor. And so now I can do a replacement one more time. So I've simplified this almost as much as I can, but I can do one more step. I have these three resistors, and even though they're on different sides of a rectangle, they are actually still in series because going around the corner does not constitute a change in current. Current remains the same. And so adding these together will just give me 15 plus 25 plus 20. And this ends up to be 60 ohms. And so I've created a single resistor and battery that is actually totally equivalent to the much more complicated setup or arrangement that I started with. Now, what I want to do going backwards is I want to kind of go from here backwards using my other rules about current and voltage and use Ohm's law to figure out how much current and how much current goes through each resistor and what the potential difference is across each one of them. The first thing I want to do is define the current using a rearrangement of Ohm's law. And so in this picture, or this circuit, I have a 120 volt battery and a 60 ohm resistor. And so this ends up saying, when I rearrange it, gives me a 2 amp current that's going to travel through this single resistor. Using Ohm's law and taking the current times the resistance, I can find that the potential difference across that 60 ohm resistor would be 120 volts, which notice is exactly the same as the battery, and it is what I expect. In a sense, as we talked about in class, as you go through the circuit, you will gain potential through the battery, and then as you go through the resistors, you will lose potential. Now we're going to go back and sort of use our information and look at this circuit here. Now this circuit is just 3 resistors in series that were equivalent to that 160 ohm. Because they're in series, there's no change in the current. All of these resistors will have 2 ohms flowing through them. And so we can then use Ohm's law to figure out the potential difference across each one of those resistors individually. It's kind of easy because the numbers, I love these numbers, they're so nice and simple. So I get 40 volts across the 20 ohm resistor, 30 volts across the 15 ohm resistor, and 50 volts across the 25 ohm resistor. It's just taking the current of 2 amps times the resistance, and that's where I got those numbers. Notice if I add these numbers up, 50 plus 30 plus 40 does add up to be 120. That's one of the things I could do to check my work, because it should add up. Now we're going to go back to this circuit, and we're going to replace the 15 ohm resistor by these 2 resistors that are in parallel with each other. Now the same thing is still true. We still have 2 amps coming through here, a 50 volt potential through here, 2 amps coming out of the parallel part, and this is 40 volts. And we found that the potential difference across the 15 ohm resistor was 30 volts. That's also going to be the same, using these rules, as the potential difference across each of the resistors that are in parallel. So both of these are 30 volts. This is 30 volts, and this is 30 volts. And I can use that to figure out, I can use those 2 pieces of information to figure out the current that flows through them. So I use the voltage over the resistance. So through here, I get a half of an amp, and through here, I get 1.5 amps. And so what you see is the 2 amps comes into this area, this branching, and it either goes up towards the top resistor or down through the bottom. In total, through the top and the bottom added together will give you 2 amps because that's how much current came in. And so still my numbers are working really nicely. 1.5 through the top, 0.5 through the bottom. Once you start getting used to thinking about these relationships, the fact that less current goes through the bottom should make sense because we want the current times the resistance to be equal to a constant value for potential. And because this has a much larger resistance on the bottom, it's going to have less current to give you that 30-volt potential compared to the 20 ohm resistor. Finally, the only thing we have to do to really kind of complete, amps, to complete our circuit, like kind of working our way back to the original combination that we were given, is figure out what the current and potential difference is across these 2 resistors up on top that had been replaced by the 20 ohm resistor. Now the current that goes through the 20 ohm resistor, which is 1.5 amps, is going to be the same as these 2 because these represent 2 in series and this was their equivalent. So they will all have the same current. Knowing what that current is will allow us to figure out the potential. The potential across the 15 ohm resistor is going to be 22.5 volts, and the potential across the 5 ohm resistor is going to be 7.5 volts. And notice if I add 7.5 and 22.5, they will add up to be 30. So I know there was a lot here, but hopefully if you look at this video, you can stop it and review it and start it up again and rewatch it. You can kind of see how we use these rules to sort of simplify the circuit and then use the rules to go back up to fill in some of the other information that we want to find.